Hello everyone and welcome to the series on mathematical methods for economics. This is where you learn the math that you need to start figuring out modern age economics and the various economic models that go with it. This is the 25th video in the series, and in today's session we will talk about some techniques of differentiation. In particular, we will start with what is known as the generalized power rule. Then we will go on to bring in a very powerful yet very intuitive, a very simple rule called the chain rule. And within this framework, we will also be talking about the concept of a composite function because that is needed to develop the chain rule. We will also talk about the generalized power rule as a special case of the chain rule. And as always, I will throw in some practice problems, some practice questions as and when possible so that you can check your understanding relating to these rules that we're going to develop in this video. Okay, let us start with the generalized power rule. Let us suppose we have to differentiate an expression of the form. Please look at the slide here where y is equal to the function g of x to the power a. Here g is a differentiable function and a is a constant. Now I'm sure most of you might have already done this in school and most of you would know the answer already, but let us suppose you did not. So if you do not know the answer, how would you approach this problem? Let us put on the hat of a researcher and let us try and think about this question, how you would differentiate this particular expression from a research point of view. Let us see if we can develop a pattern of things here. So as you can see on the slide here, let us examine things in this way. And if you want, you can think about things in your own way. You can pause the slide for a moment and think about things. In particular, if I put a equal to 1, so the constant here is, the power here is a equal to 1, that in turn would imply that y is equal to g of x, right? And we already know that when y is equal to g of x, dy by dx is equal to g prime of x. That will be the derivative, g prime of x. Similarly, when a is equal to 2, that implies that y is equal to g of x the whole squared. This in turn can be written as g of x times g of x, and we can use the product rule to arrive at the expression for dy by dx here. So dy by dx would be the first function, g of x. In fact, here both the first and the second functions are the same, so it won't matter where you start. So g of x times the derivative of the second function, which is g prime of x, plus the second function times the derivative of the first function, which is again g prime of x. So this, when you add up, these are basically two identical expressions. So you get 2 times g of x times g prime of x. Let's do one more exercise of this kind. Let's take a equal to 3. So we've done the first two already, which I've presented here. Let us now take a equal to 3 and see if we start seeing a pattern. Now, if a is equal to 3, then y is equal to g of x cubed. And this in turn can be written as g of x times g of x the whole squared, right? Now again here we can use the power rule. So if we use a power rule, then, if we can use a product rule. And if we use a product rule, then dy by dx is equal to g of x, the first function, times the derivative of the second function, which is 2 times g of x times g prime of x, plus the second function, which is g of x the whole squared, times the derivative of the first function, which is g prime of x. Now, if we just do some algebra here, we can combine these g of x terms. So we can take the product of these two terms and get 2 times g of x the whole squared, the 2 is coming from this constant here, times g prime of x, plus g of x the whole squared times g prime of x, and this then gives us 3 times g of x the whole squared times g prime of x. Some of you might have already started seeing a pattern of things here, a pattern emerging here. And if you still haven't, then let me show you these results summarized for a equal to 1, 2 and 3. And now I think things should be fairly clear. So I'll also point out the pattern. Our expression here is g of x to the power a. For a equal to 1, we get dy by dx equal to g prime of x. For a equal to 2, we get dy by dx equal to 2 times g of x times g prime of x. And for a equal to 3, we get dy by dx as 3 times g of x the whole squared times g prime of x. Now, if you notice here, there clearly is a pattern. The first thing that you should be noticing is that whether a is 1, 2 or 3, you have a g prime of x term in each one of these results. So, do you see here? Then we also have that if you look at the number up front, let's just ignore this middle term for 2 and 3, equal to 2 and 3 right now. If you look at the numbers that you have up front, you have 2 here, which is the same as the constant a that you've taken in the second case. Similarly, in the third result, you have a 3 here, which is the same as the a that you have, the value of a that you have taken in the third case. And similarly, you can extend that argument in the first case where a is equal to 1. So that coefficient is nothing but 1 itself. So that does not figure here, but that's understood. Okay, then there's another term to contend with. This term is g of x. Now, if you notice here in the second result, g of x has a power which is 1 less than the value of a that you have taken. So the value of a is 2, so g of x to the power 1. Similarly, when you take a equal to 3, you are taking the power of g of x as 2, which is again a minus 1. And similarly, even in the first case, you have actually g of x to the power 0, which is nothing but 1, so that we don't need to write. And the pattern that emerges, if you can discern a pattern here, the way I just explained, then the pattern that emerges is as follows, which is to say that when y is equal to g of x, where g is a differentiable function, g of x to the power a, then dy by dx, the derivative of this function, is given by the parameter a put up front times g of x to the power a minus 1 times the derivative of this function g prime of x. And here a is any arbitrary real number. Now, we will be looking at a more formal proof in the second part of this lecture when we talk about the chain rule and we develop the proof of the chain rule and we talk about how the generalized power rule is a special case of the chain rule. So that formal proof will be coming in the second part of the lecture. But for now, take this result as given. We will practice a couple of questions with this formula. And also, just to get a sense of the proof, what we will do is we will do 2 parts to the proof for this particular rule. One is where a is a natural number. So let us show that the generalized power rule is valid when a is the constant a is a natural number. So a is equal to 1, 2, 3 and so on. And the approach that we will take here is that of mathematical induction. Now this is our claim here, which is nothing but the generalized power rule at work. How does the principle of mathematical induction work? We will assume that we will first check that the rule is correct for a equal to 1. Now, if we put a equal to 1, what do I get? Y equal to g of x, which in turn implies that dy by dx is equal to g prime of x. And that you can see is consistent with the formula that you have in the yellow box above, where a is equal to 1. So that's 1 times g of x to the power 1 minus 1, which is 0. So g of x to the power 0 will be nothing but 1. And then you have this g prime of x term. So clearly the rule is correct for a equal to 1. Now, the way we proceed in mathematical induction is we assume that the rule is valid for some arbitrary a equal to k, some arbitrary k. And then we go on to, assuming that the rule is valid for A equal to K, we go on to prove, we go on to see if the rule is valid for A equal to K plus 1, and then that sets up a cycle of things. So if the rule is valid for A equal to K plus 1, then we have a valid proof. So let us assume that the rule is valid for A equal to K, and that then would mean that y itself is equal to g of x to the power k, and by the result that we are given, the claim that we are given, dy by dx would be equal to, because a is equal to k, I'll put a k here, times g of x to the power k minus 1 times g prime of x. So let's assume this is true, and now what we have to prove is that the rule is also valid for A equal to K plus 1. Now, if A is equal to K plus 1, then y is equal to g of x to the power K plus 1. Now, this I can write as, and this is the typical strategy that we use for doing proofs under mathematical induction. We try to bring in this assumption for A equal to K and see if we can use it strategically here. So the way I've written this function now is y equal to g of x times g of x to the power k, with the intention that I will then use the result for g of x to the power k in this particular proof. So we can again use a product rule. Dy by dx will be given by the first function, g of x, times the derivative of the second function, and that's something I'm going to take from my assumption above, which I have on top. So the result that I have from this particular assumption that is valid is that for k, g of x to the power k, the derivative is k times g of x to the power k minus 1 times g prime of x, and then plus, because we are using the product rule, the second function, which is g of x to the power k, times the derivative of the first function, which is g prime of x. Now let's collect the terms. We have g of x here and g of x to the power k minus 1. So when I multiply these, the powers will get added to get to give us g of x to the power k. And here the first term will become k times g of x to the power k times g prime of x, plus the second term written as it is, g of x to the power k times g prime of x, and this then gives us k plus 1 times g of x to the power k times g prime of x, which is exactly what we had to prove. So this rule is clearly valid, the generalized power rule is clearly valid when A is a natural number. We can also go on to prove that the generalized power rule is valid when A is equal to minus n, where n is a natural number. See, we have already proven the result for n being a natural number, and now let's see if we can extend things to minus n. So in this case, where a is equal to minus n, y will become g of x to the power minus n, which is nothing but 1 divided by g of x to the power n. Now here I can use the quotient rule. So here dy by dx, to differentiate the function, I can use the quotient rule, and dy by dx will become the denominator times the derivative of the numerator, which is 0 here, minus the numerator, which is 1, times the derivative of the denominator. That result we've already proven. That derivative is going to be n times g of x to the power n minus 1 times g prime of x. And that is then divided by the square of the denominator. So that's g of x to the power 2n under the quotient rule. Now, if I just collect the terms again, so I get minus n, and then this g of x to the power 2n in the denominator. I can take this to the numerator to get g of x to the power minus n minus 1, because n minus 1 minus 2n will give us minus n minus 1 times g prime of x. And there you are. That is exactly the same pattern of things that we had got under the generalized power rule when we were trying to discern a pattern. Right, so this is the same result, and this is to prove that the generalized power rule is valid when a is equal to minus n. Let us also look at some examples relating to the derivatives of certain functions where we can use the generalized power rule. So our first function here is given by y equal to x cubed plus 2x minus 1 to the power 10. To use a generalized, now actually you people, if you have done this in school, if you can do this directly, you can actually just do this directly. But otherwise, if you want to specify things very clearly using what we've just developed, the generalized power rule that we've just developed, then you can write y as g of x to the power 10, where g of x is equal to x cubed plus 2x minus 1. And using the generalized power rule, our dy by dx would be equal to the constant 10 times g of x to the power 10 minus 1, which is 9, times g prime of x. So that then gives us 10 times x cubed plus 2x minus 1 to the power 9 times 3x squared plus 2, because 3x squared plus 2 is a derivative of g of x, and that is then our answer. Similarly, let us suppose y is equal to square root of 1 plus x cubed. In this case, we can write y as g of x to the power half, where g of x is equal to 1 plus x cubed. In this case, dy by dx using the generalized power rule would be given by half, which is a constant, a times g of x to the power minus half times g prime of x. Now, g of x to the power minus half would be nothing but 1 plus x cubed to the power minus half. G prime of x is 3x squared. So, half and 3 I can combine to get 3 by 2. 3 by 2 x squared divided by square root of 1 plus x cubed is our result here. I have yet another example here for you in terms of math. Here in this third part of this question, y is equal to 2x plus 1 divided by x minus 1. The whole thing to the power 1 by 3. In this case, let us take g of x as 2x plus 1 divided by x minus 1 and write y equal to g of x to the power 1/3. So, dy by dx then becomes 1/3 times g of x to the power 1/3 minus 1, which is minus 2 by 3, and here in brackets I have g of x, times the derivative of g with respect to x. Now, the derivative of g with respect to x would be the denominator x minus 1 times the derivative of the numerator, which is 2, minus the numerator, which is 2x plus 1 times the derivative of the denominator, which is 1, the whole thing divided by x minus 1, the denominator, the whole squared. So, that's x minus 1 squared. That then gives us 1/3 times, now what I've done is I've written 2x plus 1 by x minus 1 to the power minus 2/3 as x minus 1 divided by 2x plus 1, to, both factors to the power 2/3. And then for the last term here, I have, see the 2x and the 2x here would get cancelled. So that gives me a minus 2 minus 1 minus 3 in the numerator divided by x minus 1, the whole squared. The 3 here will cancel out the 3 in the denominator in the first term here, and that then gives us x minus 1 to the power minus 4 by 3, excuse me, this will be a minus 1. So, x minus 1 to the power minus 4 by 3, because that's what we get when I subtract 2 from 2 by 3. 2 by 3 minus 2 will be minus 4 by 3 times 2x plus 1 raised to the power minus 2 by 3. So, I hope these examples give you a sense of things and enable you to work with the generalized power rule easily. Now, let me give you an example from economics. This is an example from the books Sater and Hammond, and it is based on a study for taxpayers in the US in the income bracket $80,000 to $120,000. Now, let us suppose that for these taxpayers, the relationship between gross income Y, represented by Y, and total income tax, represented by T. So, let us suppose that this relationship for Y and T paid by a taxpayer is given by the equation T equal to A times BY plus C to the power P plus K times Y. Now, here A, B, C, P and K are all parameters. These are all positive constants, to be more precise. The first part of the question asks you to find an expression for the marginal tax rate, which is dt by dy. Okay. Now, dt by dy is a marginal tax rate. Let us get a sense of, let us first think a little bit about what this expression means. This is a marginal tax rate. This is what we are calling the marginal tax rate, which is to say it tells us how much additional tax the taxpayer will have to pay for every additional dollar earned. So when income increases, what is the additional tax that the taxpayer will have to pay? And that then represents the marginal tax rate. Now our equation is T equal to, capital T equal to A times by plus C to the power P plus K times y. So the marginal tax rate is given by, if we use a generalized power rule, so that will be given by A times, we can bring this P up front. Now you can start doing things directly also, times by plus C to the power P minus 1. Right, times the derivative of this expression in brackets, by plus c, and that derivative is b. Here we are taking the derivative with respect to y. So that this is the equivalent of our g prime of x. So if we were to take by plus c as g of x, so in that sense we would get this result. Plus the derivative of ky with respect to y, so that's going to be just k. And we can write this expression then as A times P times B times by plus C to the power P minus 1 plus K. Now this study actually also was about finding some results, specific results relating to certain values of the parameters. So here it was estimated that A was, in this equation, T equal to A times by plus C to the power P plus Ky. It was estimated that A was 0.000338, B was 0.81, C was 6467, P was 1.61 and K was 0.053. So if these are your parameters, then the question asks you to find capital T, the tax, the total tax paid, and the marginal tax rate if y is equal to 100,000. Now T would be nothing but we just substitute all these values into the expression here along with y equal to 100,000. So once we do that, we get 0.000338 times b times y, which is 0.81 times 100,000, plus 6467, which is our C to the power P, which is 1.61, plus K times Y, which is 0.053 times 100,000. And that gives us approximately 35,869.33. So this is the total tax paid. And the marginal tax rate, similarly, you can do the same exercise with these numbers and substitute all these numbers into this expression for dt by dy, and the marginal tax rate comes out to be 0.51. So this is to give you a sense of things as to how you can actually, how one is actually using the generalized power rule in economics. With this, we conclude the first part of today's lecture. Thank you very much.